This is an example slightly more complicated than the one in class. It's regarding relative motion. Airplane is flying through the wind, which itself is moving across the ground. The distance here is 300 miles between Chicago and Cleveland. The plane flies. The plane flies over the ground, or no, the plane flies through the air in any direction, and it has a magnitude of 500 miles per hour. So you can fly a plane through the air in any direction at 500 miles per hour. Now, of course, you want to fly across the ground from here to here, directly, Chicago to Cleveland. So you want your velocity vector for the plane over the ground, you want it to point directly from Chicago to Cleveland. We're not sure how fast, we're not sure what the magnitude of this vector is, because there is a crosswind. Here I'm going to say, here's the vector, this is the air over the ground. The air is moving at 100, the magnitude is 150 miles per hour. The direction is, say, 30 degrees. We'll call this 30 degrees from the, at 30 degrees south of west. So we have 150 mile an hour wind blowing 30 degrees south of west, and we know we want to travel straight east. We're not sure how fast, what the magnitude of this vector is, but we know its direction. We know the magnitude of how fast we fly, 500 miles an hour, but we're not sure of its direction. Using the equation for relative motion, we can say that the velocity of the plane through the air is equal to the velocity of the plane over the ground minus the velocity of the air over the ground. Now, this is there's a minus vector. This is a vector equation. It's probably best to consider this as an addition problem, where we add a negative vector. And a negative vector is simply the same vector of opposite direction. So here is the vector, here is negative VAG. It still has the same magnitude of 150 miles per hour, but it's going in the opposite direction. So this is 30 degrees. Well, you can see equal and opposite angles from geometry. These are both 30 degrees. So there's our negative VAG. This is the negative of the velocity of the air over the ground. Now we can graphically represent this vector equation. We know the direction, but not really the magnitude of this, the velocity of the plane over the ground. We know we want to travel directly from Chicago to Cleveland. Now this vector we know a lot of, know a lot about. It's probably shouldn't be that long. This is the negative of the air over the ground. Now we know that the magnitude of this vector is equal to 150 miles per hour. These are velocity vectors. And we know that it travels upwards at an angle of 30 degrees. So we know what its components are. It has two components. It has a y component, which, because this is the opposite side and this is the adjacent side, it has a vertical component of, so I'm going to use sine 30 degrees times 150 miles per hour, which is approximately equal to 75 miles per hour. And it has a horizontal component, which is a function of the adjacent side to this angle, so that is cos 30 degrees times 150 miles per hour, and that is approximately 130 miles per hour. So a 150 mile an hour wind blows at 30 degrees from the horizontal, blows 130 miles per hour horizontally and 75 miles per hour vertically. Notice that 130 plus 75 is well over 150. This wind blowing at an angle blows in both directions, horizontally and vertically, and the magnitudes are related geometrically. A squared plus b squared equals c squared, not naively, where you just add them up like scalars. Alright, now we know that these two vectors add up to the airplane's vector, the plane flying through the air. So the plane flying through the air must fly through the air. It's the addition of these two vectors. Here's a vector. We don't know what its length is, but we do know its orientation. This vector, we do know what its magnitude is, and we know its orientation. This vector, we do know what its magnitude is, but we don't know its orientation. So what is this angle theta here? That's going to be the first thing we want to know. All right, now vectors add up. Now this vector, these vectors do not add up as easily as the problem in class, because they're not at 90 degrees to each other. But if we consider all the horizontal components, that would be this vector and this Vx, this horizontal component of the wind, and we consider all the vertical components, which is just the vertical component of the wind, these do form a right triangle, and we can add them up horizontally independently, vertically independently, and use them to calculate the length of this vector. So because this is a right triangle, we can use Pythagoras over this outer triangle. So we have, let's say, a squared plus b squared is equal to c squared for a right triangle.